All right. Good morning, everybody. The class today will deal with autocorrelation, triangulation, homography estimation. Okay. We will deal a little bit with a very popular application that you have on your cellular phone, which is called panorama stitching. So the idea, I'm sure almost everybody here, maybe everybody here, try this option. The idea is that you take your camera, your phone camera, you take several pictures, usually by rotating the camera, and there is a computer program that stitches the different images and create a panorama. Okay, and there are here you can see the different steps in achieving the panorama. The main thing is to achieve registration between the images, align them, and once they are aligned, you remove seams, you make them look like a single picture. So let's start. So the first question is how do we achieve registration? The main issue is that, for example, if I try to register the sky here to between the images, I won't be able to really know how to register the images, right? Because the sky look pretty much smooth and there is not much information there. This is an example that shows also that our perception of color is sort of skewed. In this slides of Olson, he tries to motivate the use of features from this. I think that this is not a great motivation, but anyway, it's an interesting thing to look at if you haven't seen this kind of picture. So you have this checkerboard, and the question is which square is darker, square A or square B? And I think you all see square A as darker. But if now I'll cover all the checkerboard except for the two squares, you will see that they actually have exactly the same color, the same intensity. Okay, and the reason we see B as lighter than A is that B is actually in the shadow cast by the cylinder. And we understand that the color is darker for B because of the shadow, and we compensate for this. So this is a sort of a nice processing done in the brain, but one that you can use to build a optical illusion on. Okay, so we want some way to understand what features we can extract for image registration. And the idea is to use something that is called the autocorrelation function. So let's look at this function. So suppose I want to find, yes, please.
Sorry, I have a question. I didn't quite understand what do you mean by register an image. Could you explain again?
Registration means alignment. Okay, you have two images and you want to bring them such that they will fit. Now, we will talk about specific fit for panorama stitching that would be fit under homography. Okay, so we will look for the best homography that puts, let's say, the left image here on top of the image to the right, right? I want them to exactly fit the pixels in one image to the pixels in the other image. Of course, that's not always possible. We will discuss this. Okay, that's called image registration. Okay, so the autocorrelation function. Suppose you want to find repetitions in the image. We can define a function that will tell you where you can find a repetition, and it's you can see here it's very intuitive. Let me see if I can use the annotation here. Hold on a second. Okay, so you take the image IU and you shift it by some amount t, some vector t. Okay, and now you simply take a square difference between the two copies of the image. Okay, that is supposed to find a repetition. So if there are symmetries in the image, you're supposed to get a minimum when I of u plus t coincide with I of u. Okay. Now, you don't want the entire image to be shifted and then find a repetition. What we want to do is to look at small areas and see if those small areas repeat. So what we do is we use a window function. Hold on a second. Okay, we use a window function. We can use a rect function or a Gaussian. And we simply modify the integral that we saw before by multiplying every element by the window function. Okay, so let's understand what's written here. Okay, again, we have the difference between I of u plus t and I of u, but now we weight this by the window function. Okay, and so the integral in the case of rect will only check if a square in the image matches the same square shifted, or Gaussian the same way. Okay, so this is called the autocorrelation energy, and of course it's a function of position u and translation t. So u is the center of a local window, and t is the shift to find a repetition. Okay, so okay, so now we want to manipulate this integral a little bit. We will replace I of u plus t by its first order Taylor expansion. Okay, and the Taylor expansion is I of u plus the gradient of the image at u times t. Okay, and replace this. So you see we have here a difference. What we should have now is the gradient of I times t squared. Okay, this is a scalar, right? The gradient is a vector. T is a vector of translation. The inner product is a scalar. You take the square of this inner product, which is written here. And you can open this, right? The transpose of this times itself, and plug it into the integral. Okay, is this clear? Let me know if any step here is not clear. Okay, and we see that there is like an important structure here, which is the gradient times the gradient transpose. Okay, so it's a vector times itself transpose, an outer product that produces a matrix, and this is the matrix. Okay, so what is the matrix? The derivative of the image with respect to x squared, with respect to y squared, those are in the diagonal, and the mixed derivative um, in the off diagonal. What can you tell me about this matrix? Anybody wants to say? Can you immediately spot any property of this matrix?
It's symmetric.
Symmetric, that's immediate. Okay. Anything else?
Yeah,
Okay.
it's also positive or
Right.
semi-positive,
Positive semi-definite.
Yeah.
Right. Exactly. Okay, it's positive semi-definite, and it's rank 1, actually. It should be rank 1 because it is produced from a vector times its transpose. Okay, but the important thing is really that it's positive semi-definite, which means that the eigenvalues must be non-negative. Okay. So let's look again at the integral with this matrix. And what we notice is that the integral is over u, the position in the image, and not over t, the translation. So we can take t outside of the integral, okay? And look at the remaining integral without the two t's here. Now we have the same matrix as before, but now it is integrated over the window. Okay, and that's the autocorrelation tensor, the structure tensor. You can also call it autocorrelation tensor. Right, so it's exactly the same matrix, same positive semi-definite matrix that we saw before, except that it is integrated over the window. Okay, which makes it more stable, let's say, in the image.
Ronen?
Yes.
Since you use the first Taylor order,
Yes.
it's all this equation is true only for small t,
Small
right?
translation, right, right. We will understand why in a minute. So essentially, we're looking for repetitions, in a sense, nearby. So the next question is, in what situation we expect a repetition nearby? Okay. One situation is the area that was the sky, right? If it's uniform, then of course, if I make a small shift, you will find a repetition, right? And essentially, that's exactly what we are trying to distinguish between, right? So if it's smooth, we don't want to use it as feature. It won't be a good feature for registration, okay? So that's exactly the idea, and we see it here, okay? So again, the structure tensor, A of u, is symmetric positive semi-definite, okay? And we can look at its eigenvalues. If the two eigenvalues are small, that would mean that we are in a smooth region. And that's exactly the case, as I said now, that if you shift your window, you see a repetition. It's a sort of like a trivial repetition, right? But that's the situation with a small region. If there is one large eigenvalue and one small eigenvalue, that could be an edge. So it means that in one direction there is repetition, and in the orthogonal direction there is no repetition. Okay, the window changes. And if you have two large eigenvalues, that could be a corner or some kind of texture, like here. This means that small moves will make changes in any direction. Okay, so we see, for example, that these bricks, you know, if I shift, if I take a long shift, I have repetitions, but that I don't care so much. Okay, at least this autocorrelation function with the Taylor expansion doesn't reveal this situation. Okay. So the situation that we have two large eigenvalues are the situation that I want to use. these will constitute features, and features I can match between images and then register the image, align them.
Onen,
Yes.
can you explain why each situation, as you described, yields this kind of eigenvalues? I mean, why smooth regions have two small eigenvalues?
Right. Okay. So let's look at smooth region. So let's look at uniform region. Okay. What are the derivatives? They should be zero, right? In the x direction, in the y direction. So if we go back to it, it's easier to look at this structure tensor without the integration. So let's go back here. Okay. The derivatives are zero. The matrix is zero or close to zero. And the eigenvalues, both of them are zero. They are small. Okay. That's what happens when it's smooth. If it's so let's take an edge. Let's say that it's in a horizontal edge for a moment. Okay, then you should have the I to the y should be large, the I to the x should be zero, right? So so here, if I rotate this, I will get one large eigenvalue and one small eigenvalue. Okay. Even if I don't rotate it, that's the case. But if I don't rotate it, I see it directly in the derivatives, in the x and y derivatives. Okay.
So the rank of this matrix is 2, no 1?
No, I didn't say that. The rank is still 1 because it's an outer product of a vector.
Oh, okay, because when you take in the integral, the second matrix is of rank 2, right?
Right, right.
Okay.
When I take the integral, it can be rank 2, can be full rank. Yes. Right. So that's a good point. Thanks. Okay. Okay. And based on this idea, there is this what's called the Harris corner detector. The idea is to use some function of the eigenvalues. As you see here, the product minus alpha times the sums of squares, sum of the square of sum of the eigenvalues. And the idea is that this functional should be high in the case that the two eigenvalues are large. Okay. So that allows you to reveal these features. And what we can do is reveal these features in one image, in a second image, and the next thing we need to do is to match them. Okay, once we know which feature in one image goes to the other, we can solve registration. Okay. So here you can see the maps that are obtained by this function of the Harris corner. You can see that essentially you get a black image, so there is no peak in the left side when the image is uniform. There is no peak even when there is an edge, but there are many peaks when there is texture and there are, corner-like features. Okay. So I want to move on to something called SIFT. I'm sure everybody heard about that. It still is, I think, a very popular feature detector and descriptor. So we will discuss it a little bit, and we'll see how it relates to the Harris corner detector. Okay. So the idea in SIFT again is we want to detect features, but also we want to match them across images. SIFT, by the way, is a scale invariant feature transform. That's the name. So here is how it goes. So first, what we do is we apply a filter that we call difference of Gaussians, or Mexican hat, to the image. Okay, so what is the difference of Gaussians? How does it look like? So think about two Gaussians, the red one and the yellow one. Okay, so each of them has a different sigma. Okay, and take the difference between them, you see that what you obtain is this blue curve. And the blue curve has peak in the center and negatives in the periphery of the filter. Okay, it's circular. And so what you expect is that when you convolve this filter with the image, that you will find some places where there is peak of intensity relative to the surroundings. Okay, so what we want is to find local maxima and minima of this function d, of this of the result of the convolution, okay, as a function of x and sigma. So with respect to both x and sigma, sigma is a scale parameter. Okay. Again, well, not again. Now, we don't want, or we would want also to find these features not only in the resolution of the image, but we want to find it in a sub-pixel resolution. So we use Taylor expansion. I didn't put the formula here, but you can sort of find the peak even between pixels. Okay. This feature transform, gives you some response also with edges, and so they did another step of edge elimination, essentially using a functional that looks like the Harris corner detector. So in a sense, they use the different corner detector, but filter that detector using the Harris corner points. Okay. And finally, looking at the window, we want to compute a dominant orientation. And the idea with the dominant orientation, if we want to allow rotation of the image, this will tell us how the image was rotated, or at least how the local neighborhood was rotated. Okay. By the way, this part is not much in use. Okay. Once we detected the features, we write a record that describe the feature. Okay, the reason to do that, what we call key point description, is that we want to then match features across images, and we hope that these descriptions will be consistent across images. Okay. So the idea with the description is the following. You take your window, you divide it into small windows, and in each small window, you compute the gradient. Okay. So this you do for every scale. Okay. And next, what you do is you create bins. So you divide, let's say, this window into 4. Okay. And in each bin, you take a histogram of these directions. And usually you weight the histogram by Gaussian, so that a gradient near the center of this bin, of this square, will be weighted more than a gradient that is in the periphery of this square. Okay, but this gives you some kind of a descriptor of the texture around a point that was detected before. Okay. Overall, you get this produces a vector of 128 numbers. And now you want to match this vector of 128 numbers across images. So you want to find features that are similar. Okay. That's the basic idea with the with SIFT. And when you match, you do the following simple thing. You take a feature, you look for corresponding or similar descriptors. If you find one point in the other image that has a similar descriptor, and all the other descriptors in that image are not so similar, there is a gap between the similarities, then this is called a unique match and you want to use it. If on the other hand, like in the case of bricks, you find many matches, more than one, then you discard this feature, you don't use it, okay? Because then you're not sure where it should go in the other image. That's the basic idea. And before we finish this, I would just say that the next step is to do ransack. I don't remember if you learned it already in this course. It was taught in the introduction. I think Yoni should talk about ransack, so we will not talk about it here. But essentially, the idea is that the SIFT descriptor give you many false matches, not only correct matches. And the reason is that it looks locally, it doesn't really use context. And so what you want to do is to apply some kind of a robust estimation of the transformation between the images. Robust means that you use many features, but many of them are incorrect and you want to discard them. Okay, and only use the correct ones. Okay. Any questions here? Okay, I'm going to make a detour and tell you a little bit about triangulation. I'm not sure why it's it's in this class, but it relates to material you learned in the last class, in the previous class. And then we'll return to the panoramas. Okay, so consider the following situation. You have an image, and I take a pixel. This could be one of the points that we detected with SIFT. And of course, with one image, we cannot tell where, at least without priors, we cannot tell what is where along this ray the pixel is. So we don't know the depth. Okay. Now, if we take a second image, of course, this ray would project to the epipolar line. You learned that. But suppose now I hypothesize that the feature on the left matches the feature on the right. Okay. So I have this ray. The depth of this point should be somewhere along this ray from the left image. But it also, if I'm correct, if these are projections of the same point, this point on the right should lie along this ray. So essentially, you expect them to the rays to intersect, and that would determine the depth of the point. Okay. So do you know when they will intersect? What? So two lines in 3D don't have to intersect, right? What condition can you tell me that would make them intersect?
The right point need to be on the epipolar line.
Exactly. That's exactly the constraint. If the right point is on the epipolar line of the left point that matches the left point, then they will intersect. Okay. But generally they might not. Okay. So how would we determine the depth if these two rays don't intersect? Of course, what we want to do is to solve some least squares problem. Okay, so let's look at that. Okay, we want to find the 2 points on the two rays that are most nearby. Okay, and we solve it with DLT. So let's see how. Okay, so what do we have here? We have two cameras, or more generally, n cameras. Okay, so PI are the camera matrices. We have a collection of 2D points, 2D projections that we think belong to the same 3D point. Okay, and those 2D points relate to the cameras by this equation, right? So xi times some scale factor, which is depth dependent, okay, equals to the camera times x, which is the 3D points. Okay, what are the unknowns in this in these equations?
The first two coordinates are fixed.
No, so let's look again at this. Okay, we know the points in the image. We know the cameras. Okay, what we don't know are the depth and the 3D position. Okay, so what we know are xi and pi, small xi and pi. What we don't know are lambda I and capital X. Okay. Of course, we could come up with other problems where we know capital X, but we don't know the cameras, etc. All of these are interesting problems, but here we consider the case that we know the 2D points. Okay, let's use annotate. We know the 2D point here. We know the cameras, and we don't know X, and we don't know lambda I. Okay. Okay, so overall, we see first that these equations are linear in capital X and lambda I. Okay, and for every point, every 2D point, we have n such 2D points. We have 3 linear equations here, so 3n linear equations. And the number of unknowns, the depth values, there are n of them. And x, capital X, is 3. So the number of unknowns is n plus 3. So if n is 1, for example, we have 3 linear equations in 4 unknowns. We can't solve that. There is no unique solution. But if n is 2, if there are at least 2 images, then we already can solve this. Okay, so we can do triangulation with 2 images. Okay. Now, the equations are linear, and notice also that they are homogeneous, right? Because you have unknowns in every term here. Okay, so we can write this as MV equals 0, okay, where we rearrange everything in a matrix. So the unknowns are capital X, lambda 1 to lambda n, and m are the coefficients, okay? So x is multiplied by the cameras, P1, P2, okay? And lambda I are multiplied by x1, x2, etc. The size of m is 3n, because that's the number of equations, times 4 plus 3n. What? Yeah. Right. So why is that? Now I need to think. So the camera is of size 4, and X
X is
X is in
X, Y, Z, and 1.
right. So, but we don't use 1 here. We use a scale factor. So X
Right.
is up to scale.
Right.
So that's 4.
That's 4.
And lambda I. So lambda I should scale every component of xi, and xi again is in homogeneous coordinates. So we write it without scale, I think. No, we write it as xy1. Okay, so every x1 here should be of size 3. I should have written x1 transpose. Okay, so we have 4. The width is 4 for the camera, and then 3 for every point. And here we have x, which is a 4 vector, and then 3 times lambda 1, 3 times lambda 2, etc. Okay.
Yeah, that's correct.
Yeah. Okay. So this is.
But if xi is horizontally, so the rows is not matches.
Right.
The weight of the side of P1 is not the weight of X1.
Maybe you're right.
So it's not.
Then maybe I'm
be
wrong here.
transposed.
I'll check it after the class, and I'll change the I'll change the slides accordingly. Okay. Let's not stop here. But I think the idea is very clear, right? The idea is to write these equations and separate the variables and the coefficients so that we get MV equals 0. And you can always do that when you have linear equations that are homogeneous. Okay. And this is sort of a standard step in many applications of the DLT algorithm. Okay, and right, and at the end, when you solve this, you need to normalize x, because it's a you normalize by the 4th coordinate so that you get 1 in the 4th coordinate. Okay, and I think, right, Merav, you taught DLT already, right?
Right.
Yes. So the solution to this is to find the null space. Generally, M wouldn't be full rank, and so what you do is you find an approximate null space using SVD and taking the singular value that correspond to the smallest the singular vector that corresponds to the smallest singular value. That would be the approximate solution of MV equals 0. Okay, and this is a solution to triangulation problems. Okay, for whatever number of points you have, right? Not only in 2 images, but in possibly n images. Okay. Okay, in the next few minutes, we will talk about homography estimation. So with homography estimation, we compare 2D points, and we don't try to find the depth, because when the relation between images is homography, we cannot recover depth. Okay, but the idea is very similar. Okay, so here we have images that are produced by homographies. Okay, so you have a VI, let's say in one image, a homogeneous 3D vector or a 2D coordinate. Okay, and you want to apply homography, so which is unknown, H. Okay, H is a linear 3x3 matrix. Okay, when you multiply VI by H, you get a new vector UI, but up to a scale, which is lambda I. Okay, and the problem is, when given UI and VI, you want to estimate H and lambda I. Okay, so this is very similar to the triangulation problem. So you can already, I think, realize how to do that. Okay, the idea is again, so the unknowns are lambda I and h, then the coefficients include ui and vi. We want to write this as a homogeneous linear equation, mv equals 0. Okay, and we do that again by writing first the unknowns. So the unknowns are here the columns of h, h1, h2, h3. So these are 9 entries of h, okay? And lambda 1 to lambda n, okay? So overall, n plus 9 unknowns, okay? And the coefficients are, so h multiplies vi. Actually, h1, h2, h3 should be the rows of h. Okay, so the first row multiply v1, the second row multiply v1 in the second row here, and the third row multiply v1 in the third row, right? And this should be equal to lambda I ui. And so what we do is we put lambda I here, and x1, y1, and 1 are the components of u1. Okay, x and y and 1 are the components of un. Okay, so these will multiply lambda 1, and these x and y and 1 will multiply lambda n. Okay, and so this way we write mv equals 0. And again, by using DLT, we can solve for h and for lambda 1 to lambda n. Okay, and let's do the counting. So we have 3n equation. We have 3 equations for every pair of points, assuming we have n pairs of points. Okay, 3n equations. And the number of unknowns is really 8 plus n. Okay, 8 because we have 9 entries for h, but we solve up to scale. Okay, up to global scale on this equation. And n unknowns for the lambda i's. And we can see that n must be greater or equal 4 in order to have solution, a unique solution to this equation. Okay, unique solution or unique approximate solution. Okay.
Ronen, is there any geometric meaning to those lambda?
Yes, but so essentially lambda is a number that tells you location along the ray. Okay, so let me just see. We will have some drawings in the next hour, and we can you can remind me this question. But essentially, think about the location along the ray, right?
I understand why lambda is the location along the ray in the triangular estimation, but also in the homography estimation.
Yes,
is the same?
Also in homography. So let's wait with this question when I show you some pictures of what's going on, and then you will see this. Okay, let's take 10-minute break if it's okay with you.
Please pause the recording. Just pause, not stop.
Okay. 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 So next we want to talk about panorama stitching. Okay. Okay, so the assumption that we will make is that you rotate the camera around its center. Okay. And so you can write the following equations, right? So given a point, a 3D point X, okay, you apply rotation 1 and then project. So you get lambda 1 times small x1. You will see the point in the image in small x1. Okay. And the same thing, you take the same x, you apply R2 and lambda 2 x2, that will be the result. Okay. And so it clearly small x1 and x2 are related by homography, which is composed of a rotation matrix. Okay. So simply if you eliminate capital X here, you get lambda 2 over lambda 1 times x2 equals to the product of the two rotation, R2, R1 transpose times x1. Okay. And x1 and x2, you can think of them as belonging to, they are in homogeneous coordinates, and you think of this as a projective spaces, projective planes. Okay. If the cameras are uncalibrated, you should multiply the homography from the right and the left by K1 inverse and K2. Okay. So you simply, in these equations, the first ones, you write K1 R1, K2 R2, and do the same procedure to get H. Okay. Then H will be general, not just a rotation homography, but a general homography. And just to, why is it homography? Why rotation of the camera around its center doesn't reveal any information about depth? The reason is simple. Look at this diagram. So the camera is in the blue points, and these are rays from the cameras. This is the image plane, okay? And the pixels are, of course, the intersection of these rays with the image plane. And now when I rotate the camera, I'm basically only changing the image plane. I don't change the rays, because the rays are determined by the focal center. Okay, that's all the lines that go out from the focal center. Okay, and this means that if this building is in some depth, some distance from the focal center, it remains at the same distance from the focal center after rotation. And so we didn't get any new information about the depth. And what we have, this projection, doesn't allow us to know about depth. And now you can see here that, so regarding to a question I was asked before, okay, so this diagram basically tells you what's going on with projective transformations, in this case with rotation, right? We take the same pencil of rays and we slice them with two planes, okay? The lambdas that we saw before are related to positions around, along the rays. But these positions, so lambda 1 is a position with respect to this plane, and lambda 2 is with position with respect to these planes, but we can't really know the actual position. We only know ratio, how they changed between these two. This doesn't give us a depth information. Okay. Okay, so the full algorithm for panorama stitching is written here. So you get several images obtained by camera rotation about the focal center. Okay, the first step is to find good features, for example, using Harris corner points or using SIFT. Then you try to find matches using SIFT. The third step is to apply RANSAC to compute homography. Okay, so the reason is that we can't apply DLT because SIFT will produce many false matches. And so first we want to discard the false matches. But once we identify the true matches, we can apply DLT also. Okay, we compute the homographies. Okay, in the calibrated case, these are rotation matrices. In the uncalibrated cases, these are general homographies. Then we register the image. So we apply the homography such that the images will align. And finally, we remove seams. So let's see the registration. So here, given these two images, we want to find the homographies. And once we have the homography, we apply homography from one image to get the second image. But the way we do it is through bilinear interpolation. So what we do is we take a pixel in one image, we apply the inverse homography to the pixel. This gives us a location that generally does not fall exactly on the grid. It falls between grid points. And so we use bilinear interpolation here to determine so what we do is we then apply bilinear interpolation to these 4 grid points. We get intensity and color for this star point. Then we apply H and we put back the color that we computed here, we put back on the new copy of the left image after homography. Okay, that would be the registered left image on the right image. Is this clear? So again, I want to take the left image and apply it to find the color for every pixel according to the positions in the right image. And so what I do is I compute subpixel positions in the left image that will get me to pixel positions in the matched image. Okay, that's the bilinear interpolation. Okay, once we've done this, we have images that are aligned. So here we have 2 images, and this is the alignment of the 2 images, just overlay of the 2 images. And as we expect, they don't really match everywhere. Okay, that depends on how accurate you were in your assumption of rotation, and maybe also the person moved a little bit. And to get a good picture, what we want is to take part of the new picture from the left image and part from the right. And that's, that would create a seam. And what we want to do is to choose a seam that has a low cost. Okay, so that's the final solution. Okay, anybody wants to suggest how to solve this problem for finding the seam? Any idea? So the most common idea is to solve something like minimal cut. Okay, so for example, a simple algorithm would be, let's take the derivatives. Okay, look at the absolute value of the derivative. We want to find a cut between the 2 images that minimizes the sum of derivatives. Okay, in this case, in this way, the seam will go in positions where, derivative, I shouldn't call it derivative, differences between a pixel in one image and the neighboring pixel in the other image. Okay, so between, let's say, pixel here in the left image, in the right image, minus the pixel here in the left image. Okay, that would be a cost on an edge in a grid. Okay, and now I want to find a cut that minimizes the sum of.
Ronen,
Yes.
why does it not take the trivial answer, just go around take only one image as a cut?
that would be good if the images were not, so you could do that if they were really completely overlapping. But what we want in the end to achieve is something that looks like this. Okay, so clearly, oh, sorry. Clearly, you know, this image would not cover the areas here. So you have to somehow stitch them. Okay. So that's why you do what I said. So minimal cut is a very common solution. Another thing that people do is to rule out the like faces. So you can see here in the red circle, they try to detect faces, and then not prevent the cut from going inside the area of the face, because people are very sensitive to changes of intensity and color in a face. So that's the end. So this is this is how you build panoramas in cell phones. Okay, in the remaining of this class, I want to go through some more advanced topics. Or I would say one is more advanced and one is more modern. So we will talk a little bit of something that is called the supercollineation matrix. And after that, we will talk about deep learning. And, you know, these are like short tours of other subjects that are related. Okay, what is the supercollineation matrix? So remember that we had like n images here, n panorama images. All of them are related by homographies. Okay, and what we did is we registered one to another, right? So we registered pairs of images. But you could think of trying to register all of them together, right? Because there are constraints. If you have homography from image 1 to 2 and homography from image 2 to 3, then that determines the homography from 1 to 3. And we may want to use this constraint, because if we estimate the homographies from features, they may not be consistent. Okay, so this is something that we call in our work averaging of different transformations. So here it's an averaging of homographies. Okay, so here is the setup of the problem. You have n images, and for every image I and j, there is homography hij. Okay, and the pixel, the kth pixel in image j is transformed by hij to the kth pixel in image I, and I forgot here the lambdas. No. Sorry. Okay, of course it's not equal, it's up to scale. Okay. Okay, so now I can take these H's and put them all in one big matrix, which we call G. Okay, so H11 is which matrix? What do you think, H11?
Would be identity.
Right? From image 1 to image 1, the homography is identity. Okay, but except, so the diagonal is identities, but otherwise hij would be the hij block, 3 by 3 block in this G matrix. Okay, and there are some constraints. So hii is identity, as I said now, and hij is the inverse of hji. Okay, that makes sense, right? Okay, now we want to ask, what are the properties of G? Okay, so so to get the properties, we need to understand what is hij, how they are related to each other. Okay, and the idea is the following. So we can take any global reference, okay, and write the following equation, hij, so h0 or 0 will mark the global projective coordinate system. So Hij is a product of Hi0 and H0j. Okay, so take the jth image, apply homography to get to the global reference, then take the global reference, apply a new homography to get the ith image. Okay, so we have these products. Okay, and that implies that we can take G and factor it into a product of two matrices. Okay, so this 3n by 3n matrix turns out to be a product of H10 to Hn0 by H01 to H0n. Okay, you see that? So the first matrix in the factor is 3n by 3, and the second is 3 by 3n. Okay. And this implies, for example, that G is has rank 3. Okay. Also, we see that, right, H10 is H01 inverse, right? So really these two factors are inverse of each other, or they contain inverse block inverses of each other. Okay, so I said that rank G is 3. The product of Hi0 and H01 is identity. And we can also see, you can check that the three non-zero eigenvalue of G are simply n. Okay, so there are three equal eigenvalue, which are n. Okay, and otherwise you have zeros. Okay, now this is, of course, if you found the homographies correctly. Okay, but there is one thing that I missed here, or, well, there are two things to say. One is I estimate the homographies from features, so they might not be consistent. They might not satisfy these equations. And also I estimate them only up to scale factor, and I need to get rid of the scale factor. Okay, it turns out that there is a simple way to get rid of the scale factor. The idea is to normalize it to have determinant 1. Okay, and that we can do by taking the determinant of Hij and normalizing by the determinant to the power of 1/3. Okay, the 1/3 comes from the size of H, which is 3 by 3. Okay, that would make every H determinant 1 and determine the scale factor. Okay, so after we do that, if they were consistent, they would satisfy this constraint that the rank is 0, the rank is 3, sorry. They are inverse of each other, and the eigenvalues are n. Okay, so that's the end of this part. So what you do is, given the feature points, you estimate the H's, then you normalize the determinant, and then what you do is you project to rank 3, okay, and factor to get the H's. Okay, so that would be a solution to finding consistent set of homographies. Okay, questions on that?
Can you explain again why do you do that?
Why to do that?
Yes.
Okay, so the idea is that you want the homographies to be consistent. You want to get a solution that would not accumulate errors in the panorama. I should say that this is a very nice paper, and this is a very nice math, and I'm not sure that this is used on your cell phones.
But again, every H already has an error inside.
Say it again. Every H
has an error inside it.
Right. Whenever you estimate H's, I mean, homographies or anything from data, you have errors, right? Now, so think about the following situation. Suppose H23 has a little bit of error, and H13 has a little bit of error, and H12 has a little bit of error. Now, these three H's could correct the errors if you make them consistent, okay? The example that I like to give is if there were rotations, for example, right? You know that once you go in a circle, you have to return to identity, right? So, so if you force this, you can reduce the error, okay? And that's good to do in general. Okay. So the last part for today, I want to talk just briefly about deep networks that are used to estimate homographies. As you will see, it's a very simple modification of existing networks. It works okay, mostly for small transformations. But overall, it's an interesting and not simple subject to make deep networks work in geometry problems. Okay, so so this is an outline of the network. The input is composed of two images, okay, and the output is homography, right? We want to find, the assumption is that the two images are related by homography, and we want to estimate the parameters of the homography, okay? So how to parameterize the homographies? A simple way is to simply think about the matrix. We want to estimate the coordinates, the entries of the matrix. We have 9 entries up to scale. We can estimate either all the 9 entries or just 8 of the entries and assume that the last entry is 1, okay? They didn't choose to do that. Instead, they chose 4 points on one image and estimated the positions of these 4 points in the second image. Anybody thinks why this is better to do than using the parameters, directly the parameters of H?
And again, the assumption that the two images are related by homography.
Yes.
Right?
Yes. If it's not, then I don't know what you will get, right? So this is I want to see. Okay.
We know the corner on the they are on the same plane.
Okay, so the idea is very simple, but this is true not only in this kind of problem. So it's good to have this in mind. When you register images, right, by homographies, there may be situation where two homographies are in their parameters are very similar, but they give you very different solution. Okay, so in the image, the effect on the pixel may be large, okay, or vice versa. Okay, and we are interested in the effect on the image. Okay, so you can think of situation where you take an image and you contract it very, you know, in a big way, for example. Okay, so the pictures here are not so good for this, but you can imagine, right? Homographies take a quadrangle and turn it into another quadrangle. So think of a quadrangle. Let's take a square and make it a quadrangle such that it's almost a triangle. Okay, this will be almost a degenerate transformation. Okay, now so when you have an extreme transformation, small changes in the entries can give you a big change in the transformed image. Okay, and vice versa. There are situations where big changes in the transformation will give you only small changes in the transformed image. We're really interested in the transformed image, right? Small changes in the transformed images are things that we want to detect, right? We don't want to So we don't care how the parameters changed. We care more how the points changed. And so it's a good practice to say, let's parameterize the transformation by points in the image. So for example, I will take a patch, maybe a big patch in the image, and I ask where the corners moved. And if the patch changed much or changed little, that the error would be counted according to how many pixels changed in the transformation. Okay. Okay. So as I said, we parameterize the homography by the transform positions of the 4 patch corners. Okay. And what they did is use a supervised loss. Okay, so the idea is that we have the parameterization of H that the network predicts, and we have the ground truth that we computed in some way. Okay, and we want to minimize the loss. Okay, so this is a simple supervised idea. Now, to compute the prediction of the network, what they did is they used VGG, the usual, the well-known recognition, object recognition network, where they change only the top layers to do regression for the 4-point positions. Okay. And they use the further quantization. So you can see here the softmax here. So basically this is binning in order to get a confidence estimate for the prediction. Okay, so this way they say, you know, in this range of parameters, I'm more confident. In this range of parameters, I think there is this is not the homography, etc. This way you can produce confidence estimates. Okay, that's the simple idea. So the network, if you try to think what it does, it takes 2 images, it applies VGG, so it produces some kind, it applies several convolution layers, max pooling, produce feature vectors that describe the images, the content of the images, and now you hope that these feature vectors can predict well, can regress well the homography. Okay, that's the simple idea. Now, a follow-up paper thought that, you know, we don't need supervised training. We can deal with unsupervised training. How would we do that? Any idea?
To take image to take synthetic homography, and then you can do it to.
Okay, synthetic homography, if it's synthetic, there is no reason to do unsupervised, because synthetic I can produce, you know, and know the solution. So why not just use supervised? I want to use real images in the training. But so if I want to use real images and I want to use supervised loss, I need to use another method to compute the homography. And that, you know, may be suboptimal. So what can I do instead?
To try to align the 2 images and then
Exactly.
and then to check the error.
Exactly. If I align it, if I find the correct homography, then the intensities of one image should be mapped by the homography to, you know, in the ideal case, to the same intensities as in the second image. And so I can simply compare the intensities or the colors. And that's what they did. They used an L1 norm, as you can see here. Sum of L1 differences between the transformed image and the registered to image. Okay, and trying to minimize that. And that's an idea that appears in many different works. If you're trying to estimate parameters where using those parameters, you can predict something. You can see how your prediction is good, right? You
But
don't have to
it
compare
sounds
the
like
parameters directly. Yes.
it sounds like if you have closed solution, so it's easy to bridge the gap. But if the
Yes.
if the alignment is too far from each other, so gradient descent will not helps here.
That's true. That's a good criticism, and I think that um, it's not clear how to solve problems that we call them large baseline problems, problems where images are far away from each other. They were taken by cameras that are different by the difference in parameters is large. But I should say also that classical methods also have problems with that. So SIFT doesn't find good matches when the difference between the pictures is large.
So if you have like a good initial point, like to start with supervised and then move to unsupervised, could help.
Yeah, you can play with that. So you can use, as Michael said before, you can apply simulations, simulate homographies and train. Or you can use just unsupervised, pure unsupervised, but you need a proper data set, right? You need data set with pairs of images that are not too far from each other. Okay.
I have
Yes.
also a question. If, let's say, because of my angle, my sensor has autocorrection of the lighting, and I have different illumination in the image. So I have a big error between,
Right.
even that I applied the homography, I still have a big error.
Yes. Right. So that's true, and people overcome this by a very simple idea. What they do is, instead of looking at the difference of pixels, single pixels, they take patches, let's say 3 by 3 patches or 5 by 5 patches, and then they take the difference after compensating for a scale factor. Okay. This usually gets rid of these intensity, big lighting differences. Okay, so that's the idea. It's called normalized. It's like a variation of normalized correlation. Okay, but you do this patch by patch. Okay. Okay, finally, why did they use L1 norm? The idea is simple. L1 is more robust than L2. And so you expect that there will be some places where there is no match. For example, one image, when you apply it, or it doesn't see part of the scene that the other image sees, and vice versa. You don't want to penalize these parts too much. So that's the idea with L1. Okay, they, like in every paper, they give some results. They look very good. They even compare to SIFT, and they seem to outperform SIFT in some conditions. I would not take that, as if SIFT should be discarded and this is the network we should use. I also, these papers are from 3 years ago, so maybe there are newer papers that are better. I didn't check lately. But we get the idea. Okay, I want to summarize. We talked about autocorrelation function and how you can use that to detect features. We talked about the Harris corner detector, SIFT descriptors, matches with SIFT. Then we talked about DLT as an algorithm to solve triangulation problems and homography estimation. We talked about how to build a panorama, problem of image registration and seam removal. And finally, supercollineation, how to solve for n-consistent homographies, and some deep networks for homography estimation. So this is like a table of content. Okay, more questions?
Yes, I have a question about the
Collineation, yes.
You talked about homography, that it means that you don't have translation between the images, only rotation.
Oh, okay, between the cameras, not between the images.
Cameras.
Okay, yes.
What happens if I have translation between the cameras?
What happens if you have, that's a great question. Not, let's start, let's start about homography in general. So if there is translation in the camera center, is there homography between the two images?
I think we can find some matrix that find how to.
Okay, but generally, I'm asking, if you find, would it make sense? Yes.
Only if it's a planar scene.
Exactly.
Or very far scene.
Exactly. If it's planar scene, if it's far scene, I'm not even sure that that would still be true. But if it's planar, that's the case. Okay. So if it happens to be planar, I'm taking pictures of a wall and I'm moving and I'm taking more pictures of the same wall. They will be related by homographies, and I can use the supercollineation to solve for all the homographies together. Okay. If I do that for general 3D scenes, the homography will not really make sense. So the fact that I'm using like Ransack would mean that Ransack would choose some of the points and estimate homography from them. So if the points happen to be on a plane, then there will be homography. But now if I try to apply supercollineation here, maybe the homography between image 1 and 2 is based on one plane, and between 2 and 3 on another plane. And so then this won't tell me much, right? So they won't be consistent by construction. So I don't want to use homographies if this is not the right model, okay, in general.
So what we can use?
So we will talk about that. You should use essential matrices, fundamental matrices. Okay, we will get to that later in the course.
Can you also explain? Let's say this slide, I got my H11 and all the others. What do I do with that again? How do I?
We just plug this cable because my battery is running low. What did you say? Can you repeat the question?
Can you explain again? How do what I'm doing with this formula? I have my, let's say, transformation from one to another. Okay.
Okay.
How do?
Right. So let's remind ourselves with the panorama stitching problem, right? So first I took pairs of images. I applied the Harry Sift, found features, applied Ransack, found some homography, and maybe use DLT also. Now I have homography between image 1 and 2, and I repeat that for every pair of images. Maybe all of the pairs I managed to find homographies, maybe some of the pairs I have missing data. I don't know the homographies, okay? Next, I'm placing all the homographies in this matrix G, and I clean it. How do I clean it? I project it to be rank 3 using SVD, okay? And so I normalize the homographies and project it, okay? Now every Hij here is given by a product of Hi0, H0J, okay? I take these new matrices, these clean matrices, and I apply the rest of apply them to the rest of the steps of the panorama stitching. So let's remind us where we were. Okay, so we're between 3 and 4. Okay, now I use the new homographies to register the image with the bilinear interpolation and to remove the seams. Okay, so the step of supercollineation will enter between step 3 and step 4 and will simply clean the homographies that I use in the next steps.
So how did you use the homography between I and 0, I0, J0, and so
No,
on?
I just use them by multiplying them again to get Hij. But the new Hij is
But you don't have them.
No. What do you mean I don't have them? I have the matrix G.
You cleaned your G function, right?
The G matrix, yes.
G matrix. Now you don't have the composition of two.
No, once you so you don't really need to do the composition. Once you project G to be rank 3, you already have Hij in the rank 3 G. Okay.
Okay.
So the factors is just to prove that that it's rank 3.
Okay.
Okay. Yeah. Okay. All right. Thank you all, and see you next week.
Thank you.
Thank you.
Thank you.
Thank you.